Now the plan. In this video we have the planning of this serial transmitter in mind, okay? That is what we have. And you know that in this chapter we talk about both the hardware circuit and the software. They go together and they are combined in the final developing and testing in Proteus. But now we have to discover how invent the hardware, what kind of connections are necessary and in which ports, for example, in which port pins, and the software that has to solve the state diagram that in some way is given in this picture. So what we have here is a detailed picture by picture, you see diagram by diagram from the very beginning to the end on how this idea of the serial transmitter can be implemented this time using C code for a microcontroller. Okay, so what goes next now is the study of the planning of the circuit. How it is possible to organize the hardware in the first place, connect the microprocessor to the power supply, to the ground, to the external oscillator, for example, 4 MHz, that is right. And then the push button, that is the clear direct or the reset or the master clear. And that unavoidable connections, along with the idea that some pins will be used as outputs and some pins will be used as typical inputs to be read. Okay, so you have some pins that will be write and some pins that will be read. All right, well, so that is the typical thing and the usual way. But here in this application, we have to detect, for example, the rising edge from the start button. Okay, when you click the start button, you generate the pulse, and you have to detect that so that the transmission sequence can start. And later, when you have detected this start button, what goes next is detecting precisely every single rising edge of the clock, so you can transmit one bit at a time. So to do that, you know that the clock and the start button are special because they are edge signals. They are edge sensitive. This is what you like, to detect exactly the active edge. Whatever, you can program that. It may be the rising or the falling edge, but you have this idea in mind, detecting the edge. So to do that, you have to connect, for example, the clock to the RB0. Why? Because this signal is also understood as the interrupt 0, and RB1 is the same, interrupt 1. And there is another pin, it is the RB2, okay? That is the other external interrupt that you have available here in a PIC18F. Because if you have picked instead of the PIC18 the PIC16, what is the difference is that if you have the PIC16, there is only one external interrupt possible, okay? So that's the difference, and this is why, for example, a PIC18 can suit us very well, because we have two external interrupts to finish with this application. All right, so very well. When the hardware is solved, what goes next, is talking about the software. And the software, you see, is exactly the same that was explained when we talk about finite state machines that were simple counters. So the idea of an infinite loop based on this organization of the software, the main loop, okay, and the main loop consisting on reading inputs, state logic, and writing outputs. Okay, this is what you will do once and again. Read inputs. This is what we call pooling. Okay, because when it happens is because this function is embedded in the main code. So every time that this function is executed, you will read the value of the external inputs. For example, this time the data in. Okay. Then the state logic to determine which is the next state to go. and then the calculation of every single output at a given state. And finally, if you have the variables correctly decided, you will write the outputs to some pins. That goes forever and forever. That is what you have in mind. And you know, because time to time someone clicks a button, you have to detect that edge, and this will happen, for example, when the system is running. Now, for example, the system is interrupted because at this time this event happened, and this is when you will go and execute the interrupt service routine, specifically for two important ideas: setting the bar, for example, clock flag, and cleaning, you see, the external interrupt flag, the hardware flag. So you will clear the hardware flag, so the hardware will be able to detect another edge later on when it happens. And you will set the variable clock flag, the software flag, to 1. In this way, the state logic can decide where to go next. That is the idea of the software organization. And this is what we do in this example and many more, okay? All the time the same way when talking about finite state machines. And the same ideas, exactly the same ideas, can be even clearer if you keep an eye on this organization of the different functions now that in some way can be represented as well using this format as sockets. You see, you have a socket for reading inputs, you have a socket for the detecting edges, you have a socket for writing outputs, and you have a socket, you see, a combinational socket, a truth table, for calculating the outputs, and another socket, you see, you can very well talk like this, another socket, another truth table for calculating the next state to go, you see. And that schema is quite convenient. Perhaps it's not that simple to write, but it's quite convenient because you see all the variables that you are requiring here in place. They are all here. This is the software. The kernel is based on this software environment, you see. This is software. And then the software, you see, which is internal to the computer, can be interfaced to the external pins by means of specialized functions. So you see, once and again, this kind of hardware and software diagram, this invention, this conceptual invention is quite interesting because you can use it once and again, and you can try to figure out your experiment, how it's going to look like from this perspective. Okay, in this way, you will never forget anything important. For example, if you think about initializing some pins to be inputs, well, you know that that happens in the init system. So this is the function that is here, just to decide which is the direction of every one of the pins that you are using in your application, and all the time like this, okay? So once the software is organized, naturally everything depends on this picture. That is the key point, and this is which is of interest here. Okay, exactly the same kind of state diagram that you've been using for all the chapter 2, now the same, but look at this. We rewrite this schema specifically to talk about, well, the special arrow that means the clear direct, very well. But then, you know, every single loop here happens when it happens, that is the point, when this is going to happen in time, when this variable is detected to be 1. For example, when you've got an interrupt and the software flag has been activated, now is when you like to go and start the sequence of transmitting bits, one at a time. But you see, you will stay in this state that you call start bit as long as this other software flag is kept 0, you see? And how long this variable will kept 0? Well, so until the clock is detected, you see? So for a full clock period, you will remain in this state. And that happens all the time. So you go advancing from one state to the next, And in some way you are wasting in every one of these states a full clock period. But this wasting of time, this clock time, is what you want, because you have a mission here, okay, in every one of these clocks. And you see, and you go advancing from one state to the next when this flag is detected. And you have a mission here, and this mission is to transmit the serial out, okay, that this time is 0 because it's the start bit, this time is the data 0 that you have captured first, and this is the data 1, you see, the data 2. So in some way you have the data in parallel captured, and then you are shifting this data one bit by bit, one bit by one bit to the output, serial output, until you finish with that. And then there is left here an end of transmission pools that you can generate. You see, in this state, like a kind of a terminal count, here you are indicating that you are finalizing the sequence. So in this state, you will stay again the same time, one full clock period, you will stay here just because you like to send these var end of transmission pools. So that's it, the typical and the standard state diagram that now instead of solved by hardware is solved by software variables. Okay, so that is what we have in mind. And then what? Well, then what goes next is the usual thing that you know very well. Specifying a variable for every one of the variable, for every one of the inputs and outputs, okay? And then initializing the system, taking care about the init system, you know, programming the trees bits. You see, if you have a 1, this is because this pin in the port B is an input. If you have a 0 here, is because this pin in the port C is an output, like this. And then what goes next is, you know, the flowchart for reading inputs and the flowchart for writing outputs, as usual, okay? So you can inspect that very well here, for example. And down there, the read inputs and the write outputs diagrams, as usual, as in P9, okay? And then why not? There is this other diagram which is of interest, okay? The interrupt service routine, okay? That interrupt service routine in some way is that simple, right? The interrupt service routine is that simple. Look at this. It's not that complicated, okay? What you've got is the idea of keeping an eye to the hardware flags, okay? This is the hardware flag, okay? For example, to detect the external interrupt 1. So when 1, if this is what has happened, that you have detected the start button active flag, this is what you do. And at the same time, you clear this hardware flag. So you set the software flag and you clear the hardware flag. Okay, that way. But if this has not happened, you have, you know, the typical if. So else, if this is not what has happened, you may ask if you are here in the interrupt service routine because you had the other one, okay, the one related to the clock. So if this is the case, you do the same thing. This time you set the software flag, clock flag, and you clear the hardware flag related to the interrupt 0, and you go to the end, okay, that way. All right, so in some way you have the pin, you have the edge detection logic, you have the possibility to block or allow the interrupt from this peripheral, from this external pin, and then the final interrupt, the general interrupt enable as well. So you may like to block all the interrupts for some applications, but in this case, you like to allow precisely the interrupts from the start button to start the sequence, and you like to allow the interrupt from the clock, okay? That's the way it goes. And finally, what is left in this plan, as usual, is the same thing that you did in the chapter 2. You have to invent in some way the state logic truth table. That's it. You have the input current state. You have this ST, that now be careful because this is the bar ST flag, and this clock is in some way the bar clock flag. So this is what is the input to the state logic, and you are going to calculate the current state in the future like that, so that after executing this function you will decide where to go. For example, if you are idle and this signal is not detected, okay, doesn't matter if the clock is detected or not in some way, because what you like is to keep the same state because the sequence has not yet triggered. All right. And later on, for example, if you are in the start bit state, this is your current state, doesn't matter if you click again the start button because the sequence is already initialized. This is already the bit 1 to the start bit, what is now on the output. So what you have to be aware is about the value of the clock flag, because if this clock flag is 1, this means that a full period of time has elapsed, and because of that you have to jump to the next state. So instead of transmitting the start bit, you will send now the data 0. The same way for a full period, right? So that is the way it goes. And finally, if you have invented the truth table, you better translate that in the usual way into a flowchart. You see, so here you see very well what kind of C instructions, cases, switches, and if and else's, basically. So you are performing operations and you have these rhomboids to know what to do, right? Something like this. Okay. All right, so that is the way it works. Well, there is always the possibility to make some variations, and then if, depending on what you are planning here, the final C software is slightly different, and that can be rearranged in any way. But you know what I mean? If you have a table, you better translate the table into a flowchart. So finally, you have to do the same for the output logic, the same way. You see, that one is simpler because basically the input to the system is only the current state, most of the cases. This is what you have, the current state. Okay, so if you have the current state, the only thing that it is necessary now is to go deciding the kind of logic value that has to be associated to every single variable, like this. All right. So if it happens that you are, for example, at the start bit, you know that the end of transmission is 0 and the serial output is 0. So that is the way it works, and the same way you transfer this truth table into a flowchart. So you know that here you have to use, because every state has a different level, you know that you have to use a case again, a structure. And that's all. What goes next is the development that we will implement, by means of a demonstration using the hardware and the software environments where we have captured the schemas and we have transferred these flowcharts into C instructions. All right.